Well, we're ready to start. First thing I want to do is go over the solution of one of the exercises, which is the data fitting one, starting from the raw data. We have a series of points, magnitude and phase, and the objective is to make the best eyeball least squares fit of both magnitude and phase points in order to get consistency between the corner frequencies obtained from both sets of data, and at the same time, of course, have asymptote slopes of multiples of the proper values, plus or minus multiples of 20 dB per decade for magnitude, plus or minus 45 degrees per decade for the phase. I'll hand out the exercise solution for this, so let's pass it around if you want to grab it. Yeah. As I indicated already, the starting point is the mid-band gain, obviously the highest gain over the whole range. So you take a flat asymptote and slide it up and down until you get the best fit over the middle of the range. And I position that at about 26 dB. So I'll identify that as A sub m, the mid-band gain. Next thing is that going towards lower frequencies, you can see that there is probably a plus 20 dB per decade range. So you take a line of the proper slope and slide that around until you get the best fit of those data points. And I position that with an intersection of the first asymptote at 100 Hertz. So this represents an inverted pole relative to the starting position of the AM. This is line number 2. I've numbered the lines because the sequence in which you do this makes a difference. The next point is that it looks as though there may be a zero down at low frequencies because there are a couple of points on the magnitude graph that seem to be bending upwards from the asymptote number 2. It's pretty hard to tell though because there's not enough points. So this is a situation where you should take advantage of the fact that the phase is a more sensitive indicator of the position of a possible corner frequency than is the magnitude. So let's change over and look at the phase data and see what we can get from that. First, we have to make sure the phase measurements are consistent with the presence of the inverted pole that we've already found. So there should be a minus 45 per decade slope centered on 100 Hertz. That's line number 3. And yes, indeed, that does fit the phase data pretty well over the second decade. However, below the corner frequency, there's obviously a considerable deviation of the phase data from line number 3. And it looks as though the phase points are pretty flat in that region, and that essentially confirms the fact that there must be another corner frequency down at some lower value. Because if there is a zero down around 10 Hertz, it will have a plus 45 per decade phase slope, and there's a considerable overlap with that from the pole at 100 Hertz, and so where the overlap exists, the phase is going to be flat. And so that's the condition that you actually use in order to determine where the zero is, because you now take a horizontal phase asymptote, slide that around to get the best fit of the flat phase data points, and that's line number 4. And the information to extract from that now is that the end of line number 4, where it intersects line number 3, is the end of the overlap. And so I could now draw the positive phase slope of plus 45 per decade, ending at the same frequency where I have the intersection of lines 3 and 4. That represents the end of the overlap, and that terminates at the plus 90 degree final asymptote. And line number 5 now identifies where the zero is, because it must be 1 decade below the end of the overlap. So that fixes the corner at 15 hertz. Now you can go back finally and look at the magnitude graph and draw in the corner, which is now at the known position. And the magnitude points, of course, are consistent with that, although we have a much better fix now on the position of the 0, having made the diversion through the phase graph. Because the corner initially was fixed by line number 4. Line number 4 was determined by 1, 2, 3, 4, 5, 6, 7 phase data points. So that's why we got a better fix by using the phase than by using the magnitude directly. Magnitude influence extends only 1 octave from the corner. Phase influence extends a whole decade. So that's how you go about fixing the asymptotes. And we've now started from the mid-band gain and gone towards lower frequencies and determined a couple of other corner frequencies. So now we want to do the same thing at higher frequencies. I'll take some of these overlays away first to avoid cluttering up the picture. And now we want to go in the other direction and do the same thing. So the first thing that happens, obviously, there is a minus 20 dB per decade slope. So sliding that line around, I position that at about 7 kilohertz. And the phase graph that goes with it is a minus 45 per decade slope. And I took away one too many of the earlier ones. There's line number 3 originally. Line number 8 is the phase slope that goes with the normal pole at 7 kilohertz. And you see there's a little bit of overlap with line number 3, which occurs because 7 kilohertz is a little less than 100 times 100 hertz. So we get a small overlap with the phase asymptote that makes a little jog. There's a small region of minus 90 degree per decade slope in the region of overlap. Certainly the measured data points seem to agree with that all right. The next thing is, as we go to even higher frequencies, obviously the magnitude levels out now, and we have enough magnitude data points to use directly to locate that 0, and I position that at 100 kilohertz. That's line number 9. So there is a 0 at 100 kilohertz, leveling out the gain. And being a 0, you'd expect it to have a plus 45 degree per decade phase asymptote, which is line 10A. And now we're running into some difficulty, because this clearly is nowhere near where the phase data points are going. So there is a major discrepancy now, and it doesn't seem possible to fit the phase and magnitude data with the same corner frequency in a consistent way. Well, you don't have to look at this line very long to recognize that the discrepancy is probably only in the direction of the slope. Having gone that far, it's pretty clear that if you just turn that slope upside down, then it looks as though it would fit pretty well. So if you try that, make it a negative slope instead of a positive one, that's line 10B, and sure enough, that fits the measured data pretty well now, over the whole range. So the discrepancy is not in a whole sequence of points, and at first thought you might think, well, you just got the wrong quadrant off the measurement of the phase. But in fact, it is consistent, and there's only one discrepancy, which is the sign of the slope. The position of the slope is correct. So there's only one thing that you have to change in order to represent all of the magnitude and phase data over the entire frequency range. And the objective, remember, is to write the factored pole 0 form and to identify the flat gains and the various corner frequencies. So we've now identified everything, and it's simply a matter of writing down what that final expression is. And that is what this shows is the sequence of construction that we've gone through already. and the equation at the bottom is the final structure. We started with the AM at 26 dB, then we went down in frequency, we found an inverted pole at 100 Hertz, and an inverted zero at 15 Hertz, and then we went up in frequency, found a normal pole at 7 kilohertz, and then we found a zero at 100 kilohertz, and that's where the discrepancy came in, and the only thing we need to do to complete the picture is to recognize that the phase asymptote went in the wrong direction for that zero, and so you'd have to represent it with a minus sign in front of the S, because that accounts for both the magnitude and the phase. The magnitude of this factor is independent of whether that's plus or minus, because the magnitude is the square root of the sum of the squares of the real and imaginary part. And the minus sign is irrelevant in that. So it correctly gives the magnitude. However, the phase, being a zero, is the arctangent of the imaginary part over the real part, and since the imaginary part is negative, then the phase comes out to be minus 45 per decade. So changing the plus to a minus is all you need to do in the final factored pole zero form in order to represent the measured data. It's a separate question as to how this sort of result can arise, because so far, at least in this course, we haven't even discussed the possibility of a zero with a minus sign. All of the circuits we've talked about up to now have been so-called normal zeros in which you have a plus sign. Now, remembering that one way of representing poles and zeros is in the complex plane, in which the left half of the complex plane means that the roots of the polynomials in S have negative real parts, and correspondingly in the right side of the complex plane it means the roots of the polynomials have positive real parts. So the zero, which has a minus sign in front of it, is known as a right half plane zero, because when you set that factor equal to zero, S has a positive real part. So that's why you have to represent the measured data by a 1 minus S. Now, the question of what sort of system can give rise to that is worth looking into, because as you see so far, we haven't had to talk about right half plane zeros, but later on we're going to have to, and this is why I've introduced it at this point. So what I'll do now is illustrate one possible way in which right half plane zeros can show up. I'm going to draw an amplifier stage, call it a blue path, call it an inverting amplifier. So we have an input signal and an output signal, and I'm going to suppose that the amplifier has a large gain at low frequencies, but it has a relatively low pole, so the gain is going to drop off maybe over some wide range, and then eventually there's a zero. This is a normal left half plane zero, a 1 plus S term, and the phase graph that goes with that, I'm going to assume a 0 degree reference, even though this is an inverting amplifier, because I have a choice. Phase reference is arbitrary anyway. So I'm going to start with the reference of the inverting amplifier and say its output is at 0 degrees. Now here we have a pole in that path, so there will be a minus 45 degree per decade phase asymptote ending up at minus 90 degrees. Then, as we get close to the zero at higher frequencies, there'll be a plus 45 degree per decade phase asymptote, ending up at 0 degrees again. That's just a normal amplifier with a pole and a zero. But now, let's suppose that in parallel with that, we have another amplifier path whose output is summed with the first one. And this is going to be a non-inverting amplifier, and it's going to have a lower gain than the blue one does at lower frequencies, but it's going to be flat, no corner frequencies. So the green path is going to have a flat gain all the way over the whole frequency range. Now it has a phase also, which will be constant, and since I've taken the inverting path to give a phase reference at 0 degrees, then relative to that, the green path is going to have a 180 degree phase change relative to the blue path. So the green amplifier is going to be fixed at minus 180 degrees. Now the objective is to construct what the overall response of the two channels in parallel is. Notice that's the sum of the two paths, not the product. So I have to add the gains of the two channels. But remember, this is the usual double log scale, dB versus log frequency. So it's not a matter of adding the blue and the green traces. But since it's a logarithmic scale, whichever one is larger is going to dominate. So it's easy to see, at least at the two extremes, what's going to happen. At low frequencies, the blue path has a lot more gain than the green one, so it's clearly going to dominate the output. So the red trace is the combination of the two, and it's simply going to follow the blue amplifier as long as the blue path has a gain much bigger than the green one. And the same is going to be true for the phase. Obviously, the phase of the output is the same as the phase of the blue path as well. So it's going to look like this. Then jumping to high frequencies, the positions are reversed. Now the green path has a gain bigger than the blue one, so the combination is dominated by the green one in magnitude and in phase. So the only part we're not sure about now is what happens in the transition. So a good guess would be you just extrapolate these asymptotes. So at least it's going to do something like that, because somewhere it's going to change over from the blue path to the green one. And so the simplest thing to guess is that you just extend the asymptotes until they intersect. That's what the magnitude would look like. Now, what are you going to do with the phase? And you don't have much choice, because we've got to go from minus 90 to minus 180 with a slope centered on the frequency that's identified as the corner frequency in the magnitude. And obviously the only way you can fit that with a standard building block is a minus 45 degree per decade phase asymptote. So the final result is you have two parallel channels dominated by the blue one at low frequencies, dominated by the green one at high frequencies, and the only way you can fit the two together is by representing the transition as a 0 in magnitude with a phase lag, which is a right half plane 0, because this is exactly the configuration that we had in that exercise with the data points. So that's one possible way in which a right half plane 0 can show up in a real system. I think it's easy to see physically how that happens, because you have an inverting amplifier at low frequencies giving you a flat gain, and it changes over to a non-inverting amplifier with another flat gain at higher frequencies. So you have to go through a full 180 degree phase reversal as you go from one flat gain to another. And the pole has to be left half plane. It has to have a phase lag, because if you have a pole in the right half plane, the system is unstable. That's where Nyquist stability criterion comes from. We'll talk more about that later. So to get from one flat gain at low frequencies to a lower value at high frequencies with a phase reversal, you have to go from 0 to minus 90 degrees with the pole first, and then you have to go another 90 degrees of lag for the 0. So a right half plane 0 is the only way you can accomplish that. So that's one possibility. And the reason I wanted to go through that exercise solution right now is that pretty soon we're going to come across a place where this actually happens from a different direction.